talk about what you are going to see for the next 5 days. So I am just giving the overview of the content of this workshop, so that you will come to know what we are going to see in this one. Okay, and then tell about what is organic electronics. I just to give you a small introduction about that, and what is a big deal about it. Why is it so important? And when you see that electronics, generally you will compare what is the current one. Current one is based on the silicon electronics. Okay, so there we develop all those things. Comparing to silicon electronics, how this organic electronics different. So when the term itself is organic electronics, you know that electronics something deal with the carbon atoms. So here the central part is carbon. We all generally know that carbon means we know polythene, everything is an insulator, but carbon also can conduct, because we know that carbon will take a different allotrope. For example, if you see the diamond, it's nothing but one of the allotrope of carbon, which is very hard material. This one in all the materials hard. And the other thing is graphene. Graphene, we know that is another allotrope of carbon, which is conductive. We know that. And there are different varieties of C60 now, nanotubes. There are a lot of things called out. So different, it's all varying, depends on what structure it takes. According to the structure, the property will change. So that it was believed that carbon is an insulator, but carbon also can conduct you. In particular concept is semiconductor. Even silicon also semiconductor, it's not a conductor. There is according to band gap theory, there is a different variation. What is conductor, what is semiconductor, what is insulator. We have a band gap theory we can explain, and we are going to see those things in this lecture. And we want to clearly make a difference between the silicon and organic. Then only we can understand. And some of the electronics and all the charge conduction process, photophysics, is slightly different from silicon electronics. In silicon, we talk about hole and electrons. Here we talk about polarons and bipolarons, different things. There are different terms, but equivalently both are same. Okay. In silicon, we talk about valence band, conduction band. Here we talk about oxidation and reduction. So those type of difference you should make clear here, so that this topic will be easily understood. Okay. And also in this lecture, I will give you a brief introduction of very important organic electronic devices, such as organic photovoltaic. That's the main device. Next thing is organic LED. This is one of the application of organic electronics. Then OFET, organic field effect transistor, is another one, because these three components are transistor and diode, which is a very basic component in electronics, and how these devices are work using the organic materials. Okay, those things we'll touch in this introduction, and we'll see everything in detail in the coming lecture. Okay, before continuing, okay, where I am coming from? I am coming from this Melbourne city, is in Australia, the southmost part of this, and there is a capital of the state is called Victoria. So this is the city center. Our university is located. This is our university campus. It's located in the city center, and this is Melbourne University is one of the #1 universities in Australia, and in the world level, it's one of the around between 25th one actually. It's the best university. Many people prefer to come over here, and we have all type of courses running here. Okay, and this is a city in the heart center. Then this is my Bio 21 Institute, where I am working, our research institute, and this is our lab and the institute inside. So my lab is located in 4th and 5th floor, where we are doing research. It's all, even if you see our building itself is all glass, everything is a glass, and we can see through what we are doing. It's a transparent building actually. All those things, people can outside what we are doing inside. So this is one of the iconic building in Melbourne actually. Okay, so this is overview of the course. So today I'm going to talk about introduction, this session. After that, in the afternoon, I'm going to talk about how we can design, because as I said, everything depends on the material. We have to use a proper material, because in inorganic, if you say the silicon is only a single atom. Everything is nicely, and there is no. When you come to carbon, not only carbon, is a basic organic material is a hydrocarbon. Carbon will come with the hydrogen, and also oxygen, nitrogen, sulfur, all atoms together. We can't make entirely carbon. Only the graphene only is a carbon, but all the organic small molecule with the mixture of carbon, hydrogen, nitrogen, oxygen, all those, how the intermolecular interactions work and how this property, that we are going to see that. And so next we once we make the material, how we can characterize this material. Because what are the material we synthesize? Because this material we can synthesize in the laboratory and check the property, whether it's got an important property. What are the characteristics which determine the good organic semiconductor? That I am going to in the third lecture. And other one is dye-sensitized solar cell, which will be covered, Professor Anandan you will take. And then I will do the photophysics. Because all this OLED and organic photovoltaic mainly depends on interact with the optical in light. This is all another kind of optoelectronics. All the electronic device deals with the optics. It's called optoelectronics. How, for example, in OPV, it will harvest all the light, but in OLED, it will give the output of light. Both are is inverse process. One is absorbing, one is emitting light. So these are all optoelectronic devices, and how the photophysics is different in these organic devices. And then I talk about OFET, organic field effect transistor is one class. And then is mainly I will go to about 2 classes to discuss about what is organic photovoltaics, what is the mechanism, and what is, because why I am giving these 2 classes, because this is one of the, some of the emerging field, a lot of research is going on. Now the current world is requiring renewable energy. We want to get, in 2050, we want to have a zero emission. If you want to proceed that level, we need to develop any renewable energy. So how this organic electronics can contribute in those aspects, I am going to talk about in this 2 lecture. And then I will talk about organic light emitting device. This one you already know that. Then interface engineering. Interface engineering is very important topic, because why, because even though all those active layer, all the process happening in the organic layer, like whatever is light harvesting as well, the light emitting is harvesting, but those everything's the charge injection and charge extraction is happening through the external circuits. Those things we still use the metal, say inorganic. Either we use silver or aluminum or gold. Still this organic material will interface with the metal to get the charge out. So how the interface work? We need to interface should be properly aligned. Otherwise, a lot of the resistance, the interface resistance will involve, and device performance will be degraded. So we need to carefully design the interface engineering between organic and inorganic. That's important concept. So those I will discuss in this interface engineering organic electronics. By this time, you will understand the whole importance concept of organic electronics. Then final end we will have the open discussion, and we'll discuss if you have any questions in the thing. And this lecture also, I will go through the lecture. If you have any questions there, you just note down. At the end of the lecture, I will give the time to ask any questions. That's okay. I will continue the lecture and note down any questions. Okay. Obviously, you get a lot of questions. So not only in this session, when you go for tea or lunch, that time also you can ask me anything else. Okay. You are free to ask. Don't hesitate me, because if you hesitate, you can't learn anything. I'm just to make you free. Feel free to ask any questions so that you can get clear about whatever the question about this research field. Because so many things is unknown. Even I'm also learning. I can say that. I'm just sharing what is available in research, what I learned in the last 14 years, because I'm in the field for last 14 years. Okay. Okay. So as I said, organic electronics nothing but is device. Any device which have the organic material as a semiconductor is organic electronic device, and the same device called in different name. One is printed. One is printed electronics. Printed electronics, because this organic device, one of the biggest advantage of this technology is, in silicon, we make everything is high temperature process, because if we have the molten silicon and make a big chunk and cut the silicon and make polishing, then everything is a crystalline. Okay, the manufacturing process is consume lot of energy, as well as it will have a lot of temperature. Okay, and also is a laborious process, and also we need to have a strict conditions to produce the silicon wafer actually. But in organic, we just synthesize the material, just to take it and mix with the organic solvent. We make a blend, and blend just to coat it. We can coat in spin coating, or we can print like how we are printing the newspaper, or like this slot dipole. I will discuss those things as well. Like this, the manufacturing process is very easy. That's why this is one of the biggest advantage of this technology. Okay, easily print, and everything is a printable actually. Then we measure the device. So that's why it's called different name, printed electronics, and polymer electronics means now we have developed not only material, organic material can be polymer or small molecule means, you may heard about what is, you already know the difference, what is molecule and what is polymer. If it is repeated chain is called polymer, if it is only one monomer is called organic materials, okay. If it is polymer electronics, if it is other things, plastic means there is another word for polymer, you can also plastic. Everything is the same name, but giving the different name. So don't worry when you hear this type of different words, all are meaning the same thing under organic electronics, okay. And what is the main difference? Why you can compare that this classical electronics come from silicon or any gallium arsenide, any silicon inorganic based. This is organic electronics. So ultimately the advantage is the reduced cost. Why the reduced cost is the manufacturing cost is very simple and reliable and cheaper because it's a lot printing process and it's a solution process. That's why it's a reduced cost. This will take a high manufacturing cost. And also, as I said, now this is a simple process. This is a complex process of involving a lot of high temperature process and all ambient conditions for fabrication, this one. So this will become flexible because organic materials are flexible. This is rigid. This is one of the great advantages because if we have a rigid surface, if we have all the solar panel, we can install only one place. But if it is flexible, we can make it any surface, in a sense, okay. Then easily do large area, but in classical electronics, we can have only 10 by 10 inch that will be connected together. We can't make large area. And this is integration. So of course, we can make extreme high density. This is not like that. And switching time still, time is very small. The organics is comparing to silicon, the organic switching time is slightly lesser. That's another disadvantage. And reproduces reduced performance and is a high performance. Of course, why I'm talking about high performance means because it's inorganic, it can withstand for high temperature because this is based on covalent bonding, which is very strong. But all the intermolecular interaction in the organic is van der Waals bond, is a very weak bond. That will make, when you take it high temperature like 80-100 AE, it will start moving. That's the basic of organic. So that's one of the things you see the material chemist is still solving how we can arrest this one, okay? So that's why it's a reduced performance I'm talking. Okay, we are not, right now, we are not competing silicon. So organic electronics just is complementary. Where we cannot use silicon electronics, there we can organic. For example, silicon is somewhat rigid if you have a solar panel. So that we can install one place. You can't take it wherever you want. But if you have any like organic electronics paper, you can take it, fold it and take it wherever you want. Suppose we go for trekking, you take this paper, then if you want to charge mobile phone, you charge lightning, you can use for temporary purpose actually, like this. So, which can act as a complementary to silicon. It cannot, not immediately replace entirely silicon. That's one, you don't need clear about this one. We are not competing with the silicon. Okay, so these are some of the things which show organic material where the application. In photoconducting, it will act as a LED and photovoltaics, and also photocopiers. And then solid state, we also go into transistor, organic transistor, and also sensor. Sensor is another good area because this is carbon is compatible to biological body. It can easily implant into them. Now some of these implant are monitoring sugar or anything or pulse people are using for embedded devices. That's called wearable. There is another field is called wearable electronics is going on. That basically using organic material. Okay. Then is metal, we can also use batteries and other things. Now we use polymer batteries also people are developing. And biological interface we do. And these are some of the applications of these organic materials. Okay, why? This slide shows that why we really need to push this technology further. So one of the things is, if you see this, the CO2 emission in the last 20-30 years is slowly increasing. Now in 2021, it says 37 gigaton CO2 is emission. So this is because of our industrialization process and every transportation. Our CO2 emission is improving. So this will reflect in the temperature. How our global warming people are talking about, we can see that how slowly our temperature is increasing from 1880 now to 2020. It's almost more increasing. If we increase in further, it will be dangerous for our human life in this planet. So we have to control. That's why the recent summit, they said until 2050 they want to have zero emissions. If you want to do that, we have to go for renewable energy. Okay, this bar chart will tell you that what is our consumption right now. It's mainly all transportation still we depends on petroleum, all car, and also the industries also they have the things. Even though we have other renewable energy, still we use fossil fuels still. So still we have 70%. This is not good. So in future this will be, you have to reduce it. So what we can do about this one? So this is another thing, because there is a lot of industrialization and transportation, which is a main cost, which causes our, in Antarctic side, the ice is melting, it will create our sea level rising, okay? And also if you see the energy consumption in future, which is keep on increasing. So it depends on your population growth, according to your age, then 50% increase world energy by another 2050, we increase another 50% from comparing now. So if you want to compare this one, we have to develop another source of cheap energy, okay? So another thing is we can see motivation. We need to energy bar totally 8 billion people. So if you have 2010, we consume already 16 terawatt. It will increase to 17 terawatt in 2050. So your energy demand also increasing, and the consumption also going on increasing. So for example, if you want to for 10 terawatt, for example, so that will release 25 billion metric ton CO2. If you go in this rate, we will finally populate the atmosphere with the CO2, it finally improve our global. So the alternative for this one, we already have renewable energy like wave energy and wind energy and photovoltaic and also the hydropower. All these things are there, but this is not enough. So solar energies have huge amount of influx. We have 120 terawatts, but we only need 70 terawatts. If you compare the energy we are receiving at Earth, it's far more than what we need. If you harvest just 1 or 10% of this energy, will make enough for our purpose. So solar energy is one of the alternative to solve all this problem. So anyway, silicon is doing that, but the manufacturing process and whatever the phase is going is still not enough. We need to find something cheaper. Okay. So how our things can help here? So as I said, it can find not only one application straight away. It can have many purposes. If you have the curved surface, even car, anything, if you go for outside tenting and use a backpack, if you want to have hiking or anything else. So this is one of the pictures taken out from San Francisco, is from bus stop. The bus stop is come with the things, the bus shade. We can also install those things. And also implantable devices. So like this, we can find many applications wherever. And one more thing is, these things you can use the indoor application as well. So now, a lot of electronic device like Internet of Things, you may have heard about this one, is a lot of power at indoor. And organic electronic, that material also we can design. You can harvest energy from this sunlight. Even every night we use light at home. That light you can harvest using this organic photovoltaic, because as I said, another problem, as I said, so if you see other things, you can do many. If you have Internet of Things, wearable devices is up to 100 watt, and again it will go up to semi-transparent OPV device, because this type of OPV device, we use very thin layer. Another advantage, silicon is, we have make more than micron level thickness, it's all opaque. But organic is working only 100 nanometer. Why 100 nanometer? There is a technology issues which I will discuss why. We can't make more than 1 micron, everything less than micron. The whole device structure is a very thin device. It's called, we can call it as a nano device, we can call, okay? So this device, when you have a thin, it almost look more than 50% is transparent. So that some of the device in mall and all, the top you can put, you can easily harvest light. The daytime it will have a transparent sunlight, at the same time it will harvesting energy. And also we have the grid-like plan. Again, when you go for this power conversion efficiency in large devices, these devices are working well at laboratory scale. Now currently the efficiency is close to what silicon says at lab scale. Lab scale means I'm talking about 1 centimeter square, this small, sorry, 1.5 centimeter square. If you go this technology in large area, so then technology, the efficiency slightly drop down. That's because of the the conducting sheet resistance of the ITO and everything else, that's another issue. So the performance is slightly go down when you go for larger area. So those things we need to address in this, okay? That's one of the conversion. Another thing is high performance semiconducting materials, stability. As I said, this organic material is highly reliable on very weak forces like van der Waals force or hydrogen bonding, that's weak. So when you apply high energy into that, it is become unstable. So those issues also we need to address this one. But if you use indoor doesn't give that much energy, very less energy, then this device will be stable. That's why this technology we can use mainly for indoor applications where we need energy and everything else. All this below 100 watt. Okay. And the major advantage is, as I mentioned already, is the fabrication process is simple. We can make a large area process. Simply spin coating. I think you may know about what is spin coating. Spin coating means just the substrate we put a solution and spin it at a very high speed. Then we can make a very thin film on any substrate. That's called spin coating, because making coating like spinning the substrate, that's called spin coating. And the doctor blade is nothing but just by coating with a small blade. Just to put a solution and coat with a flat knife edge. That's called doctor blade coating. Then also we can do evaporation. Evaporation is a standard technique because we just use a mask and high temperature we evaporate material and it will deposit that evaporation. Then printing, like printing is same. We can use various printing, the slot die and screen print all the printing technique we can follow. It depends on how thickness you want the material. Okay, and also I said is low temperature process. All these things are attractive. That's a main advantage of organic electronic devices. Okay, and also is compatible with the inorganic semiconductor because I said this material will interface to the metal to extract the charges or inject charges. Okay, then we need to improve the mobility and, as I said, stability and environmental stability. This is all the currently issue, but slightly improved. But comparing to the silicon one, still less this stability. That's one of the issues. Okay. Next thing is, this is a three important device in organic electronic devices. One is OPV, organic photovoltaic. The other one is OLED, organic light emitting device. These two devices use one of the layer is transparent because then only light should come out. So we inject the charges here and the light will be emitting this middle portion, then is come out. In organic photovoltaic, we use ITO and aluminum, these two electrode, and in between the organic line. The sun will pass, the ITO is a transparent conductor, so that light through penetrated in, then exciton will be generated here, then exciton will be, is nothing but as a whole electron bound charges which will be separated at this interface and we extract the charges. And in addition to this, OFET is not three electrode technology. You know that OFET is gate electrode and also source and drain. So these three things, organic can be usable. Okay, in this all the three electronic, this the active layer is for organic material. Okay, okay. If you see the short history of this electronics, the field is actually started in 1950. 1950, they really don't understand where we use for this technology. They just found some organic crystal, whether it is conducting or non-conducting, it's not sure about that time. They say that it's organic crystal they form. In later 1917s only, in organic photoconductors were developed. Mainly is a company called Kodak. Kodak is mainly is we may not know that we have the Kodak camera in previous days, and we have all the photographic film or Kodak is a famous company. They work on organic photoconductors, and that time only 1977, one scientist from Japan is Sarawak. He found that conducting material is a polyacetylene is one of the conducting material. In 1980, the nonlinear optics. So again the Kodak group only the first time they using the conducting polymer, the first time that demonstrated organic light emitting device. There he used the CuPC as the donating material and terephthalene as acceptor. They make one of the OLED, and the first paper published in 1987. It's from Kodak. That's the first organic electronic devices is a light emitting device. Then after that, the famous group is friend group is Holmes, and they at Cambridge University. They published the polymer light. So these material paper small molecule. And 1990s from Cambridge University, they published this one is light emitting device. Later in 2000, Nobel Prize was awarded for this conducting polymer because they made a significant, they recognized the importance of polymer. So far as you see insulating materials, carbons can be conducting. That's called conducting polymer, polyester. For that, it's a Nobel Prize award in 2000. And after that, they're also in 2000, the organic solar cell, they made the efficiency of 15%. After that, 15 years in 2017, they reported for 13%, and 5 years is 15%. Now is this efficiency is keep on increasing. Now it's reached up to 20.8. Now if you see that similar to polycrystalline silicon cell is around 21, 22. If you go single crystal solar cell is at 26 around this one. So the performance is now close to silicon. Okay, this technology. But main challenge is how we can take this. This is a laboratory scale device. How we can take it to the lab scale to the large scale and applications. The challenges is going on right now. Okay, so this is some of the evolution of this organic electronics history. And what is this materials, or what is importance of this material? We can, since this material is not, there's a lot of opportunities. Now, if you see anyone is organic chemistry, you understand how the synthesis, we can make a lot of permutation and combination, CC bond and CC double bond and carbon nitrogen. We can make a lot of materials and make. If you understand how this, the carbon, how the intermolecular interaction, how is a molecule working, then we can design the material, the property we want. Next class, we are going to see that one, how we can, efficient material can be designed. But I'm saying that that property can be tuned by changing the structure of the molecule, what we are synthesizing. Okay, that's one of the flexibility we have in this one. The other one is solution possible. As I said, these materials are soluble in organic solvent. It can be soluble in ethanol or chloroform or toluene, any solvent. So it will be a soluble. If we have a liquid soluble form, we can easily print. So that's the advantage of here. Then material can be semiconducting materials. It can be small molecule pentose and acid, and also it's a conductive material, so like PEDOT-PSS and the polyaniline. So these are all the material can be used for electrode to extract the charges. And some of the dielectric materials are PMMA. This dielectric will be used for a field effect transistor. We need to have an insulator between the conductor and the source and drain, the dielectric, and other material. And also this also can be a luminescence concentrator and electrochromic devices. And also this is another advantage, electrochromic. So electrochromic now, if you travel any of the flight like Dreamliner, one of them, if you see that the window is electrochromic, you can switch a line. I think this is one of the application device. Now right now they put it in. So by applying electricity, you can conduct the transparency of the windows. Now windows, now we have to normally, we close the door. We know it. By applying voltage, we can make it black or we can use transparent. That's called electrochromics. So electrochromics also coming from organic electronic devices. Okay, these are all devices called printable devices. Where it can printable means we can flexible is a photovoltaic device, and flexible devices display. Now in future you can wonder you can do the e-paper, we can also get it, and OLED already is all come at flexible, and the flexible batteries also coming, and organic sensor. So these are all some of the applications, and the smart RFID. These are all is flexible material and which is printable. Okay. Okay. As I said, in 2001, these three guys, Alan Heger and Len McDiarmid and Shravakov, so they got Nobel Prize for conducting, they invented in conducting polymer. Actually, the original, the first things reported by Shravakov in 1977. Okay, this one. After all this, Alan Heger is joined. Many people tried and working on, basically the first one is polyacetylene and that material, then finally awarded. So since 2000 onwards, this field is picked up and now is slowly growing, and a lot of good applicable devices and application is coming out from this organic electronics. Okay, so the very first device is this one, this guy, Ching Tang from Kodak. So Kodak only, this, the first devices they reported. In these devices, what you do, the CPC is one of the organic material, is copper phthalocyanine and perylene tetracarboxylate. This is like a donor. Like in inorganic, we talk about is a P-type, N-type material. P-type means more electron rich, N-type means electron accepting group. So you know what is. So if you have here means CPC means like P-type, we call it as an electron donating group, and This n-type is an electron accepting group, we call it, p and n-type. So they make this a p line and n layer heterojunction and make a metal on top of it and this indium oxide. So when they connect the electron field, then it emits light. They demonstrated this luminescence, electroluminescence by using this material and Chingtan. So this is after they developed this type of electronic devices flexible based on this technology. And if we talk about the main difference, we little bit understand about the energy structure, okay? Everyone knows, I remember, what is band. So semiconductor is worked on the band structure, okay? If it is we know that for metal, both valence band and conduction spells are overlapped so that easily the electron can be conducted, because in metal there is a lot of free electron. There is no barrier to conduct inside the electron. That's called conduction. But in semiconductor there is a gap. If the gap is up to less than 3 electron volt, then it's called semiconductor. If it is exceeding 3 electron, we call insulator. That's called. Okay. So this is a band structure. So if you're comparing to, because here we are using only one atom, silicon. So the band structure is very simple. But in organic, if you come here, each atom have a discrete energy levels. Okay. We have, because the frontier orbital, if we have, each orbital can have 2 electrons. At the same time, every electron cannot have the same energy level. If it is only spin up, other electrons will be spin down. So those energy different. So each electron have 2 electrons. If you have one atom, we have 2 electrons. So if you one atom with the electron with another atom, the energy level again split up. It become 2. Okay. Again, if you have more, we have more multiple electrons will come up. The energy level is split up according to how many atoms are interacting. Like this is HOMO energy and LUMO energy will be split up. If you have a nanocrystal energy, when you have a more atom together, then we have a continuous band. So this is a basic principle of band structure. So when atoms are brought together, this energy level split up and make a continuum process. So that's called band structure. One is valence band is a completely occupied band. This is some of the empty band. So that's difference you should understand for this one. So this is some of the organic structure where this carbon is conducting. What makes carbon is conducting? We know that carbon CC bond, and we know that what is C double bond, C double bond C, then C triple bond. We know that all that basic of sp3 hybridization and sp2. So these are all basic, your high school chemistry, you know that. If you have sp3 hybridization, it's only sigma bond, it's completely insulated. But if you do sp2 hybridization, this is a single bond and double bond, single double bond. If you use, so only we have 2 sigma atom and one unhybridized p orbital that will interact, that will make electron is delocalized. Delocalized means the electron is set to free, because in sigma bond the carbon is tightly bound, see it can't move. But if you have a pi bond, pi electron, somewhat electron is free, their electron is moved, start. So if any material like this, double bond, single, double bond, single, double bond, single, if it is continuously, it's called this conjugation. If any material it's maintain this conjugation, then there is a channel for conduction, then it will become conductivity. That is a basic mechanism why carbon is conducting. If it is a conjugation is there, it will conduct. If the conjugation break, it doesn't conduct. So when you design the material, we need to make sure that these materials are maintaining the conjugation so that electron can conduct in the process. Okay. And when in conduction, there will always lattice vibration will be there, and how this electron will interact with the vibration. The vibration is called as a phonon. Then electron will interact with the phonon. The electron-phonon interaction will call as nothing but polaron. So normally that's why we cannot call it as exactly as electron. Electron-phonon interaction we call polaron effect. But still for simplicity we call it as electron and holes like organic. We don't know. But we have to understand that in organic electron is really is not electron, this is a polaron effect. Okay, the charge carriers mainly. So this is some of the things, pentacene, how the structure is. This is a thiophene and we have continuously, and how these pi orbitals are changing like this. So in molecular level, what is going on, we got to understand like this. Everything, there is a pi conjugation is maintained in this organic layer, that makes the carbon is conducting. Okay. So another thing is, just now I said, this is sp3 hybridization, this is called sigma bond. But there is one unhybridized p bond. That is in p. I think you all know that what is SPDF is a subcell. In S cell you have 2 electron, and P cell you have 6 electron. All the 6 electron we go px, py, pz. Each orbital have 2 electron, right? Px. So In sp2 dibonding, one pz will be free. So that will interact, that called pi bond. Okay. So the sigma bond is highly energetic because highly strong. That's why we have the sigma bond is the energy level is very big. But when you have a pi bond, the electron is delocalized. If you saw the energy band gap is become very small. Pi and pi star is very small, whereas the sigma bond is very very large. So when this atom together interacting that, then it will have the continuous HOMO level, continuous LUMO level. When for many, this is for, you can understand what is happening in single atom so that we can really understand what's going on when multiple atoms are interacting together. That's become, what do you mean by HOMO level means again you can say is highest occupied molecular orbital. This is lowest unoccupied molecular orbital, which is same as what we are doing valence band and conduction band. Okay, okay. This is one how is organic semiconductor. This is a conjugated polymer where we can single, double, coming. This one of the example is polyacetylene, is the simplest conducting polymer. There we can have double bond, single bond. This chain will be increasing. So these are all polymers conducting. In contrast, if you see this polyethylene, we have all single bond. This is completely insulated. This is we are making our polythene bag. Normally, this is that is non-conductor. It's only for, it's a flexible. But you can see what is the difference between this and this. This is non-conductor, this is insulator, this is semiconductor, conductor. So now you have to get a point that the carbon is material conduct if you maintain the conjugation. Single bond, double bond. Even triple bond also okay. sp hybridization will make a triple bond. Any single bond or triple bond, anything, these all make the conduction process in organic material or any polymer materials. Okay. I hope you understand how this material is conducting. Okay. And again, I said something previously. Now again see that in depth, what is real different, how the binding energy, everything else, a little bit. So as I said, the silicon is single atom is covalent. Every silicon atom is tightly covalent linkage, very strong bond. Okay, that's why we can get the single crystal. Whereas in molecular crystal is van der Waals type attraction. We know van der Waals is not like strong comparing to the covalent bonding. It's a very feeble bond. So, and we say that charge carriers are free holes and electron. We know that holes means nothing but absence of electron is called holes, is a plus, electron is minus. And charge carriers are here are polaron type. Polaron is nothing but the same electron which will interact with the phonon, which is the lattice vibration, is called polaron in this case. But many cases we talk about the same as electron and holes only. But you have to understand this polaron type. And again, mobility. You know what is mobility? Mobility is the velocity of this charge carried under the electric field. How fast? Under electric field, that is velocity v by f, the electric field. So that's called mobility. That will define how the charges are moving fast in this semiconductor. So this mobility is 100 to 1000 centimeter square volt in silicon. But here is just 1 maximum is, but actually it's less than 1. Something is 0.02 to 1. So mobility is slightly low in this molecular crystal. And the effective charge carrier is very less in this case. Effective charge carrier means this only single atom, electron is free to move. There is nothing to interact. But when we come to organic case, it will move under the interaction of the other atom. So the effective mass will be very high in this one. And the band type is a charge carrier transfer. Here the band like transfer like valence band, conduction band transport. Here it's talk about is a hoping type concept. Hoping means it will hope from one point to other type. Is hope like how the frog can move from one place to, like this is hoping transport here. Okay, and the exciton is a 1 year type. What do you mean by 1 year type exciton means? This exciton is nothing but is a particle with have a bound plus and minus charge, because exciton is a neutral particle which has a plus and minus charge. This charge will recombine, exciton recombine will give the light, energy is light. If it is separate out, plus will go separate and minus, then we can separate the charge. Because any material, the organic material, the light portion, the light incident on the organic material, first the exciton will form. Exciton will nothing but as a bound plus and minus charge. So plus minus, it will be entirely 0, the total charge will be 0, but initially the exciton, after that the negative electron will be separate from this exciton, then hole will be free, electron will be free, then charge will be separate. We will talk about in this in detail. You understand this exciton is In inorganics, the exciton, the plus minus, the interatomic distance is very high. But in organic crystal, it's very bound charges. This charge are bound. Because of bound, it's very difficult to separate out. We need to do, that's why in order to separate this exciton, we need to make these organic electron devices very thin devices like 100 nanometer. Whereas in silicon, the exciton is very big, so we can make a very thick 1 micron meter devices and all. I will explain to you later as well. And also this binding energy. This binding energy is between the plus and minus is very low, only 10 millivolt, but in this case 800 millivolt. The binding energy is very high. That's why it's very difficult to separate the charges in this one, in our organic one. And also it has a high melting point, whereas it's a low melting point, because here the interaction is covalent type. We need to have more energy to melt these things. So this is some of the basic difference in this inorganic and organic material. And other thing is we just little bit go about what is silicon. If you see silicon, this is a silicon crystal. Here if you dope with the boron, this is p-type silicon. And in p-type silicon, if you case of the valence band and conduction band in arranged, where this Fermi level is close to the valence band, is a p-type conductor. In n-type silicon, the Fermi level is up. So this is very basic, you know that I know. So Fermi level is nothing but the energy required to move the electron from this to vacuum level. So you all understand what is vacuum level. Vacuum level is nothing but how to move the electron inside the surface to is the top of the surface. Vacuum level is nothing but on surface just a few nanometer above from the surface is called vacuum level. Okay, but actually electron just out of the surface, but it's really just a few nanometer in the surface. That's called vacuum level. So if the electron is inside the material, how to bring out the electron in outside the material? That's called Fermi energy. Okay. So then then electron will come to the surface, then it will become free, then it will lead for conductivity. Okay. So in this case, so as I said here, this is a semiconductor low homo valence band and conduction band. If incident light is coming, then this atom, then electron will go to the conduction band. So the electron will be here and the hole will be here. Still these charges are together only. One is electron is here and hole is here, conduction is here. So if it is hole, is only the hole is nothing but a vacancy of electron is called hole. Then it can call this hole. If the electron is go up, this is called electron. So together it will call it a exciton. Exciton is nothing but is a bound hole and electron together is called exciton. Okay. In other words, in molecular crystal, we can call hole is nothing but oxidized. What is oxidation and reduction? If anything, if you remove the oxidation, the electron get removed. If your electron is removed from any molecule, it's called oxidized. If you add any electron to the atom, it's called reduced. Okay. If it is anything oxidized, then it's called hole. If it electron add into the things, then it's called electron is a reduced form. So exciton is both are existing. It have both holes and electron is still bound charges. It's separated, but it's not completely separated. It's still bound. So this electron only, then it will move out. It will separate in organic electron devices. In OLED, the exciton will combine and make a. When you combine, the energy will be released. The release energy will come up a light. It depends on the band gap of the material. Okay. And this, as I said, 1 year type exciton type. So I said this is holes and electron. In 1 year mode type exciton, this holes and electron is still bound, but the distance is very large. When the distance is very large, the probability of separating these charges is very easy. Whereas if you see the molecular crystal, it is very bound charges here. Comparing to this and this is very, very close together. When the plus and minus is close together, it is more attractive. It's very difficult to separate out. Okay, that's why we need to use a different concept to separate out. So this binding energy is around 1 electron volt 3 binding, but this is very, very less. 10 million electron volt. This one binding is only 10 million. This is 1 electron volt 1000 million electron volt. It's nearly 1000 times higher energy. Bound energy is there. So that's a difference between this inorganic exciton as well as the organic type exciton. Okay, so we got to understand this one, then only understand this type of binding energy concept, then only how we can design the material so that we can harvest this exciton to get a useful device. Okay. Okay, this one highlighted this organic and inorganic crystal, we have continuous energy levels, where in molecular crystal we have the discrete energy levels, and in the discrete energy will become continuous. Still understand, the band gap is still excite both inorganic as well as organic. In organic we call it as a HOMO level and LUMO level. Here is a valence band and a conduction band, both are. Okay, so now I'm going to talk about the little bit about the energy band structure. So if you see the energy band here, vacuum level, we can call it, this is P type and this is N type. If you see, this is we call ionization potential is nothing but valence band energy level in the inorganic semiconductor, and the electron affinity is called conduction band, another one. The same thing in the molecular semiconductor we call is oxidation potential or called HOMO. HOMO is, as I said, highest occupied molecular orbital, which is nothing but oxidation potential. The same thing in inorganic is called valence band, and in the conduction band is called LUMO, is unoccupied, lowest unoccupied molecular orbital. Unoccupied, the molecule is, because the lower band is completely occupied, then it will, the molecule will go to HOMO to LUMO when you start conducting. Okay, this unoccupied. So how these things, how this we define these energy levels? So we have to come back to our electrochemistry. In the electrochemistry, we know that oxidation potential, reduction potential. We know that every material have the standard electrode potential. For example, if you see the, I think you learn about simple battery is called, if you call zinc copper battery, zinc metal has standard electrode potential of -76, okay? Because -76 means, so if you leave the zinc, it will ready to emit, ready to give out electron. Minus means is give out electron. If you say copper is 0.34 plus 34, it will ready to accept electron. So what will happen when you connect zinc and copper together, then electron flow through the zinc to copper, then we'll get a charge out of, that's called, all the zinc copper battery we get a charging out because of this natural effect, because zinc will readily give an electron, because that's because of standard electrode potential of zinc. So like this in semiconductor, it will call it as oxidation and reduction potential. So if we call gallium arsenide, this semiconductor, this oxidation potential is 1 and 0.5 and reduction potential is 0.1. So here the reference is like standard hydrogen electrode. I think I understand that you already know that some of the concept of electrochemistry. So electrochemistry, the reference point is standard hydrogen electrode. They make it, that is 0 volt, that is a reference. Comparing to the hydrogen electrode, how much electron ready to give. For example, if it is a gallium arsenide, it is -0.4 is a reduction potential, and gallium arsenide is 1.4. Like this is a difference. So these are all we are getting in electrolyte, in liquid state, because all the metal will immerse into electrolyte, then we conduct. But actually in our devices, everything in solid state, right? We are not dealing with the liquid state, because in electrochemistry, in battery, everything we have the electrolyte is we use electrolyte and two separated conductor, and liquid electrolyte we use. So we use ionic conductivity. But in our case, we have the electronic conductivity because we use an electron to conduct the things. So solid state. When we compare this this ionic conductivity electricity, the ionic conductivity to electronic conductivity. So the 0 level in solid state, in solidity we can call it as a vacuum level. As I said, the vacuum level is move the electron to the inner surface to the surface of the electron is called a vacuum level. So when you standard and normal hydrogen electrode both are same. If it is in electrochemistry 0, in vacuum level it's equal to -4.5. So this is a Fermi level actually. So in this case, if it is above the case is oxidation, if it is below the case is reduction potential. Okay. Some cases we need to, because when we define what is the energy level of this material, normally we go do the cyclic voltammetry to find what is HOMO and LUMO level. Cyclic voltammetry we do the liquid state in electrolyte, but when we convert this data into the solid state, so this is a conversion factor, everything's 4.5. We need to add a 4.5. Then we get what is valence band, conduction band. In other words, it call it as a HOMO level and LUMO level. Because if you want to make this energy levels are very important level. Why? Because if you want to absorb some, I will come to the point second. This energy, according to the energy level only, because if you want to OLED, if you want to emit some green light emission, so the green light is emitted some 550 nanometer. So 550 nanometer corresponding to the band gap we converted around around 1.6, 1.7 EV. So if you want, then we need to choose the semiconductor. It should be a band gap of 1.6 volt. Then only you can be able to emit this green light. Like this, whatever the application you want, according to that, at what band gap material you need to make. So that type of definition you got. How we can characterize that characterization, we need to find out, because you are doing the characterization in liquid state, but actually the device is working in the solid state. How we can convert it? So this is another conversion. This one of the things will convert from liquid state to the solid state of this electronic band. So we will do the tutorial this evening later, and also we do the hands-on experience on how to determine the energy levels in tomorrow. You will understand more about this one, okay? Because the energy level determination is very, very important, okay? And this is just now I said the comparison with P and N type. Remember, when you in transistor in PN junction diode, you know that if you have the P junction and the N junction, when you join together, some of the P won't go to the diffuse into the N level at the junction, and the N type material, some of the electron move to the P junction. So there is a depletion region formed at PN junction, okay? So that will get the built-in potential. So those will form in inorganic, but in organic semiconductor, it's not, don't have that type of free electron, that something different is forming, okay? You got to understand. So that's why there is no free charges here, okay? Okay, now we just see when we conduct metal and this vacuum level is combined to what will happen. This is the Fermi level, work function of this metal. This is the EF level. When you come to semiconductor, we have both valence band and conduction band. These levels are like this. Suppose if you join this metal and semiconductor together, what will happen? So this is when you, okay. So when you join this together, the Fermi level will be aligned. For example, here the Fermi level is here up, here is down, okay. When you join together, this level should move up, because this Fermi level should align. So when this Fermi level is aligned, so ultimately this band should be moved up. If you compare here and here, so this level should move up. That's why we got a band bending. Because of this band bending, the electron is moved from here and here. So there is a built-in charge form. So the difference between this voltage is pi m and pi m. And this type of depletion layer will cause the band bending. It will make the charge transport easier actually. For metal and semiconductor junction, it will make the conduction process easier. And if you see that another P-type, N-type junction, so now in this case, the energy is slightly up, this type N-type material, the metal work function is there. Ultimately, when this energy is high, the electron is preferred to move from to here, then this Fermi level should go down. So in that case, this level is slightly bent down. So in previous case, it was going up because energy level different. So here when the electron is transferred here, this is going down, this band bending is formed. It's forming the space charge layer. And the same thing, if you compare, in N-type it will going down, in P-type it will go up, because the other side we saw it is going up. So finally, this type of depletion region will form. So this time we will explain how is the band bending formed, because when you join metal and semiconductor together, there will be there is a transfer of charge will happen. There will be a depletion region will form. The depletion region will make a space charge of this one. Okay, so this one eventually, when you have the when you make a diode, so when you apply the positive bias, so we need to exceed this junction potential to make the charge conducting, or in reverse bias it will be a non-conductor actually. So this is some of the basic concept about PN junction diode. So this is like, as I said, like no, this is a P-type, N-type. When you combine this P and N-type, some of the P charge will diffuse to the N-type, and some of the electron will diffuse to the P. This is called depletion region. Okay, so in the N-type, in P-type things, the Fermi levels are low, and the conduction band, the Fermi levels are up. When you join together, there will be band bending here. This will make the charges from N to N-type is a drift condition, and other side make a diffusion current. Okay, that's why we make, when you apply the positive charge, at particular this when you have the positive bias, when the charge is exceeding this junction potential, it will start conducting. But if you have the negative bias, it won't conducting at all. This is the basic principle of how diode work actually. It only conduct in the positive bias. Diode you can conduct is a one-way traffic. It conduct charge in one way only. Other way it doesn't conduct. So this diode only is working we using in the organic LED as well as organic photovoltaic. It's nothing but PN junction. It's nothing but it's a diode. It's a sort of diode, but working on light emitting as well as we call this a light emitting diodes. That's a word. So this is a basic principle of how this diode is working. So based on this one, some of the transparent anode, how the diode is manufactured. We need to have the transparent anode and light emitting material and cathode material, and we combine together. When you apply the charges in this anode and cathode, then holes will be pushing through here and electron will be, then holes and electron will join together, then then it will recombine and give the exciton. Then it gives the light. So this is the very first one, organic LED. We use a TPD as a P-type, this N-type material, and we apply the voltage, it will emit the light. So the mechanism is simple. In the P-type, we inject the holes, and N-type, we inject LUMO and electrons. So this electron will travel. This is the recombination region where this plus and minus will recombine and emit light. This emission, whether it's a green or red or blue, it depends on what band gap material we are using. According to the band gap, we can get the required light. So basically, this is a mechanism actually used. Okay. Yeah, this is another one. This is another band theory. So this is we are injecting holes and electron. Finally, it, inside the active layer, it got emit and electron. So this is a very basic, simple mechanism. So it's just the recombination of holes and electron will give the light energy. Then it will come up with the required wavelength. That depends on your wavelength, the band gap of the material we are using. Okay. Okay. So this another example is a OFET, organic field effect transistor. Here we use this semiconductor material on top of source and drain and gate. This is a dielectric material. So this conductivity can be tuned about what voltage we are applying here. We know that the gate will be used to control the charge flow in the source and drain. We will see in detail in Wednesday how the OFET and all the device. Just introduce that this device work. And also there are a lot of applications based on this OFET. And organic field effect, there is a lot of applications where and all it will be used. And organic photovoltaics also is one of the applications of this one we can use. So in OLED is charge recombining. Here the exciton, we need to separate out the charges. So you got to understand now the exciton. Exciton is a bound positive and negative charge. So that we can, so that we have to either separate or recombine. Okay. So with this one, I will finish this class about introduction part. So in next part, we will see, this is some of the device that we use in our lab, where we use all the printing technology on the things. This is one of the printer of the almost 1 kilometer printable devices. Or this we have set up in Melbourne. So next class we see that design and development properties of organic. So far you have some idea about what is organic electronics, what we need. It's all basically a material property. Okay, if you tune the material, then if you adjust the material according to the material property, we can get what application we want. So next the lecture I will talk about how we can design the organic semiconductor of the required, whether we want to design for OFET or design for OLED or OPV material. Everything is slightly different because all working mechanism different. Okay, so those some of the designing at it, the strategy we will discuss some of the things. This is mostly is on chemistry anyway. Everything is chemistry, but designing is all something about physics or material scientist aspect, material science aspect. Okay, I don't most of chemistry. I only have some design concept only. Okay, I will try to reduce the chemistry part here. And before that, I just want to know who is working in at least in organic electronic research or already know some idea of organic electronics. So that can you just raise the hand? Organic. So anyone else working? Or it's okay. Anyone they know some idea about things. Oh, biosensor, no. So others? Perovskite. Perovskite is slightly photoluminescence. Okay. Okay. Or anyone is this organic, even synthesis, even chemistry, I'm not worried. Synthesis, organic material or organic chemistry? Okay, anything? Okay, good. Okay, you are in donor. Okay, what's synthesization? Small molecule or polymer? Is it? Oh, small. Okay, but have you made any application yet or no? You are only synthesis. Okay. Okay, solution. Okay. Okay, I have a few things. So mostly all are PhD students or anything or masters. Okay, because I try to reduce the most advanced. So I just give some of the basics before going to any high. That's why I want to know in what level. So this is only introductory. I hope some of the things come from even the PN junction and all. Is I said you understand because these are all high school chemistry. We need to recollect those concepts because it's very important to know what's happening. If you want to know how the device basically is functioning, is all PN junction, and how the band structure, because band structure is inorganic and organic slightly different. If you understand the different, then only we can really understand why it's not working, why it's working, so that we can, at least we understand. I said exciton. Exciton is a basic for both OPV and OLED. One is, so why the exciton is here is bound and here is very loose. Those concepts I'm taking about. Okay. If any question you can ask me, we'll continue in the afternoon. So next class, I think Anandan will take care of. Okay. Okay. Thanks. See. Any question?